On a summer morning in 2012, several hundred people packed into a lecture hall in Switzerland, and some of them had slept on the floor in the corridor outside to be in the room. What they had come to hear was a number. When it was read out, an 83-year-old man in the audience took off his glasses and wiped his eyes, and everyone stood up because a book that had been opened since the 1930s had just been closed. 13 years later, that machine is still running under the border of 2 countries, and in that time it has produced 3 separate results that look like cracks in the foundation of physics. 3 doors, standing open at once, in the best stretch that field had seen in a generation. So did they open the door to a new reality? By the end of tonight you will know exactly what happened to all 3, and why the honest answer has almost nothing to do with any of them. Get comfortable, subscribe if you haven't already, and stick around, because the thing that finally closed the biggest of those 3 doors turns out to be far stranger than the door ever was. Let's get into it. Part 1. The morning the book was closed. There is a room in Switzerland where, on a summer morning in 2012, a group of people stood up and applauded the end of a story that had not ended. The room is CERN's main auditorium. It is not a grand space. It has the tiered seating and the slightly tired carpet of a university lecture hall anywhere in the world, and on most days it holds a few dozen people listening to a talk about detector calibration. On the 4th of July 2012 it held several hundred, and it had been full since before dawn, because graduate students had brought sleeping bags into the corridor the night before, and lain down on the floor outside the doors so that they would be in the room when the numbers were read out. Some of them had worked on this for their entire adult lives. A few of the older people present had worked on it for longer than the students had been alive. What was about to be announced was the discovery of a particle. That is how it was reported, and that is how almost everyone in the room understood it. 2 enormous detectors, built and operated by 2 separate collaborations who deliberately do not share their analysis with each other, had each found the same bump in the same place in their data, at a mass of about 125 billion electron volts, and each of them had reached the threshold that particle physics uses to say the word discovery out loud. Peter Higgs was sitting in the audience. He was 83 years old. He had written the paper that put his name on this thing in 1964, when he was 35, and for most of the intervening half-century the idea had been an elegant piece of theoretical bookkeeping that might or might not correspond to anything. When the second presentation finished, and the room understood what it had just been shown, he took off his glasses and wiped his eyes, and the applause did not stop for a long time. I want you to hold on to that image, because we are going to come back to it at the very end of tonight, and when we do, it is going to mean something completely different from what it meant in the room. Let me tell you about the machine that produced those numbers, because the machine is the other main character in this story. Underneath the farmland and the vineyards on the border between France and Switzerland, at an average depth of about 300 feet, there is a circular tunnel 17 miles around. It was not dug for the machine that occupies it now. It was excavated in the 1980s for an earlier collider, and the new machine inherited the hole, which is why the ring is exactly the size it is. The tunnel had to thread its way between the Jura Mountains on one side and the bed of Lake Geneva on the other, and it is tilted by about 1.5 degrees to keep the whole loop inside a single stable layer of rock. Inside that tunnel are 1,232 main bending magnets, and those magnets are cold. They are held at 1.9 degrees above absolute zero by 96 tons of superfluid helium, which makes the inside of that ring colder than the space between the stars. Interstellar space sits at about 2.7 degrees above absolute zero, warmed by the leftover heat of the beginning of the universe. The machine under Geneva is colder than that. It is, as far as anyone knows, the coldest extended region anywhere in the observable universe, and we made it, and it runs underneath vineyards. Through the middle of those magnets run 2 pipes, each one holding a vacuum 10 times emptier than the space between the planets, and through those pipes, in opposite directions, run beams of protons. The protons are moving at 99.999991% of the speed of light. At that speed, a proton goes around the 17-mile ring about 11,245 times every second. Each beam carries roughly the kinetic energy of a 400-ton freight train doing 90 miles an hour, and that energy is concentrated into a thread thinner than a human hair. At 4 points around the ring, the 2 beams are steered into each other. About 40 million times per second, protons collide. That is the instrument. It exists because of a hole in a theory. By the end of the 20th century, physicists had a description of the fundamental contents of the universe that was, by any reasonable measure, the most successful piece of science ever produced. It could predict the outcome of experiments to more decimal places than any other theory in any other field. It had never been caught being wrong, and it could not explain why anything has mass. That sounds like a small technical gap. It is not. Mass is not a minor property. If the fundamental particles had no mass, they would all move at the speed of light, and nothing would ever bind to anything else, and there would be no atoms, no chemistry, no stars, no you. The theory that explained everything else in exquisite detail simply had no account of why the ingredients of the universe are heavy. The solution proposed in 1964, independently and almost simultaneously by 6 different people working in 3 different groups, was strange enough that it took decades to be taken entirely seriously. The proposal was that space is not empty, not the space between galaxies, not the space between atoms, not the space in the room you're lying in right now. The proposal was that there is a field spread through every cubic inch of the universe, and that particles acquire mass by interacting with it. The way a person wading through water acquires resistance that a person walking through air does not have. If that field exists, it must be able to ripple, and if you hit it hard enough, in the right place, with enough energy concentrated into a small enough volume, you should be able to knock a single ripple loose and watch it decay. That ripple is the particle they found on the 4th of July, 2012. Now I want you to notice something about how that was received, because it is the hinge of this entire video, and almost nobody remarked on it at the time. What the room applauded was described everywhere as the discovery of the last missing particle, the final piece, the closing of a book that had been open since the 1930s, and in one narrow sense that is exactly what it was. But the actual content of the discovery was not a particle. The particle was only the evidence. The content of the discovery was that empty space is not empty, that there is something present at every point in the universe, including the point where your hand is resting right now, and that everything you have ever touched or been made of is heavy because it is dragging against that something. That is not a footnote. That is one of the most extreme claims anyone has ever made about the nature of reality, and it had just been confirmed by experiment twice, independently, in the same morning. And a room full of the most careful people on Earth stood up and applauded it as an ending. They were not being foolish. Every single person in that room could have written down the mathematics of a field for you on a napkin. They knew what had been confirmed. But knowing something and feeling it are different operations, and what the room felt that morning was the satisfaction of a puzzle completed, not the vertigo of a flaw disappearing. In the 13 years since that morning, the machine kept running. It ran at higher energies, gathered enormously more data, and it began to produce numbers that did not fit. 3 of them, from 3 different quantities measured by 3 different collaborations. Each one was announced as a crack in the theory. Each one was reported somewhere in the world with the words new physics attached to it. Tonight we are going to follow all 3 of them, from the first hint to the final answer, and I am going to tell you exactly what happened to each. And then, at the end, I am going to give you the honest answer to the question in the title of this video, which is not the answer you are expecting, and which has almost nothing to do with the 3 anomalies at all. But before any of that can make sense, you need to know precisely what it was that these 3 measurements were supposedly cracking. You need to see the inside of the watch. Part 2, the watch, and its 19 numbers. I want you to picture an antique pocket watch, the heavy kind, brass, the kind that sits in the palm of your hand with real weight to it, and ticks with a precision that feels almost stubborn. If you pried open the back of it, you would find gears, dozens of them, brass and steel, meshing with springs and levers, every single piece cut for a purpose, every movement following from the movement before it. Nothing in there is decorative. If you were patient enough and careful enough, you could take the entire thing apart on a felt cloth and understand it completely, because it is made of parts, and the parts are what it is. For about 400 years, that has been the working assumption of physics. Take the thing apart, find the pieces, understand the thing. It worked on the solar system, it worked on the steam engine, it worked on the cell, and when we turned it on matter itself, it kept working, right down through molecules to atoms to the things inside atoms, and every time we cracked something open, there were smaller pieces inside, exactly as the method promised there would be. The result of doing that for a century is the theory we're going to spend tonight testing. It is called the Standard Model of Particle Physics, and I want to lay it out plainly, because the whole story depends on you knowing what is actually in it. It contains 17 fundamental particles, that is all. Everything you have ever seen, touched, eaten, loved, or been made of comes out of 17 entries on a chart. 12 of those 17 are matter particles, and they come in 3 sets that physicists call generations. The first generation is the one that builds the world. It has 2 quarks, called up and down, which bind together in 3s to make the protons and neutrons in the nucleus of every atom in your body. It has the electron, which swarms around those nuclei and gives us electricity and chemistry and every chemical reaction that has ever happened inside a living cell. And it has the electron neutrino, a particle so reluctant to interact with anything that trillions of them are passing through your chest right now, and through the earth beneath you, and out the other side without touching a single atom on the way. Those 4 particles are enough. With just those 4, you could build a universe indistinguishable from this one, and yet there are 2 more generations. The second generation has the charm quark, the strange quark, the muon, and the muon neutrino. The third has the top quark, the bottom quark, the tau, and the tau neutrino. And here is the part that has bothered physicists for 90 years. The second and third generations are exact copies of the first in every measurable property except mass. Same charges, same spins, same interactions, just heavier and unstable, decaying away in millionths of a second or less. Nobody knows why they exist. Nobody has ever produced a satisfying reason for there to be 3 of anything. When the muon was first pulled out of cosmic ray data in 1936, the physicist Isidore Rabi is supposed to have reacted with 4 words that people in this field have been repeating ever since. Who ordered that? The question has never been answered. It is not that we have a bad answer. There is no answer. There is one more thing worth saying about the 3 generations, because the strangeness of it gets flattened by the way it is usually drawn. On a chart, the 3 generations sit in 3 tidy columns, which makes them look like a pattern, like the rows of the periodic table, which turned out to encode something real about how electrons stack up around a nucleus. But the periodic table's pattern had an explanation waiting underneath it. This one does not. There is no underlying structure anyone has found that says 3. There could have been 1 generation. There could have been 7. Experiments on the decay of the Z boson tell us with high confidence that there are exactly 3 light neutrino types, and therefore 3 ordinary generations, so we know the number is 3. We simply have no idea why the universe stopped counting there. The remaining 5 particles carry the forces. The photon carries electromagnetism, and because the photon has no mass, that force reaches across the entire universe, which is why you can see a galaxy. 8 kinds of gluon carry the strong nuclear force, which glues quarks into protons. The W and Z bosons carry the weak force, which drives radioactive decay and, crucially, the first step of the fusion reaction that keeps the sun burning. Those 2 are astonishingly heavy for force carriers, around 80 and 91 billion electron volts each, which is roughly 86 and 97 times the mass of an entire proton. That heaviness is exactly why the weak force is weak. A force carrier that massive can only reach about 1,000th of the width of a proton before it has to disappear again. And the 17th entry is the one from the auditorium. The ripple in the field that fills space. That is the watch. 17 pieces meshing. And it works. I want to be very clear about how well it works, because everything that follows only matters against this background. The standard model has been tested for 50 years by thousands of people, with increasingly cruel instruments trying to break it, and it has never been caught in a clean error. It predicted the W and Z bosons before anyone saw them, and they turned up with the right masses. It predicted the top quark before anyone saw it, and it turned up. It predicted the field that gives mass, and 8,000 people spent 30 years building a machine to look, and it turned up at almost exactly the energy the fits had been pointing to. In one specific case, the magnetism of the electron, it agrees with measurement to about 1 part in a trillion. That is like predicting the distance from New York to Los Angeles and being off by less than the width of a bacterium. So here is the uncomfortable question. If the theory is that good, why is anybody looking for cracks in it at all? Because of the confession. And this is the part that rarely makes it into the coverage. Open the back of the watch again and look at how it is actually assembled. The standard model contains at least 19 numbers that it cannot produce. They have to be measured in an experiment and then typed into the theory by hand, and once they are in, everything else follows beautifully. But the theory has nothing whatsoever to say about why they have the values they have. Those numbers include the masses of the 9 charged matter particles, the 4 numbers that describe how quarks mix into each other, the 3 strengths of the forces, and a couple of parameters describing the field that gives mass. If you also want neutrinos to be heavy, which they are, the count rises to 26 or more. 19 numbers, minimum. 26 if you're honest. Every one of them an input rather than a result. Look at what those inputs look like. The electron has a mass of about 500,000 electron volts. The top quark has a mass of about 172.5 billion electron volts, which makes it roughly 340,000 times heavier than the electron, and about as heavy as an entire atom of tungsten, all packed into something with no measurable size at all. Meanwhile, the neutrinos are so light that the best current experiment can only say their mass is somewhere below about 0.8 electron volts, which means the top quark is at least 200 billion times heavier than the lightest particle sitting on the same chart. It is worth pausing on what a free parameter actually means, because the phrase sounds technical, and the reality is almost embarrassing. It means that if you handed the standard model to an alien civilization that had never seen our universe, and asked it to predict how heavy an electron is, it could not do it. Not approximately. Not to within a factor of 1,000. The theory has no opinion at all. You have to go and weigh 1, and then write the answer in the margin, and only then does the machinery start producing predictions of legendary accuracy about everything else. The theory does not know why. It has never known why. It just holds the numbers. And then there is the omission, which is so large that it usually gets mentioned as a footnote, precisely because there is nothing useful to say about it. The standard model does not contain gravity. Not a weak version of gravity, not an approximate version. There is no working quantum description of gravity at all, and there has not been one since the 1930s, when people first noticed the problem. The theory that describes everything describes 3 of the 4 forces you have ever experienced, and leaves out the one that is holding you to your bed right now. So the honest picture, before we go any further, is this. We have a mechanism of extraordinary precision, assembled from parts that fit perfectly together, which cannot explain any of its own dimensions and is missing an entire wall. That is the object that, starting in about 2001, 3 separate measurements appeared to crack. The first of them concerned 1 particle and 1 number, and the number was a wobble. Part 3. The particle. Nobody ordered. Let me introduce you properly to the muon, because for the next hour it is going to be the most important object in this story, and almost nobody outside physics has ever thought about it for more than a minute. The muon is an electron that is too heavy. That is the entire description. It carries exactly the same electric charge as an electron. It has exactly the same spin. It feels exactly the same forces in exactly the same ways. If you took an electron and asked the universe to build you another one, but 206.8 times heavier, you would get a muon. There is no other difference anybody has ever found. Because it is heavy, it is unstable. Left alone and at rest, a muon survives for about 2.2 millionths of a second before it falls apart into an electron and 2 neutrinos and is gone. In human terms, that is nothing. In particle terms, it is an extraordinarily long life, long enough that muons created by cosmic rays smashing into the upper atmosphere routinely make it all the way down to the ground and pass through your body. Several hundred of them go through you every minute, right now, quietly, and always have. Nobody knows what the muon is for. That is not a figure of speech. In a universe made entirely of first-generation particles, everything would work. The muon adds nothing that is needed. It was found in 1936 in cosmic ray tracks, at a time when physicists were looking for something else entirely, and when Isidore Rabi heard about it, he asked his 4-word question, and 90 years later the question is still sitting there. Here is the property that turned this useless particle into the most sensitive instrument in physics. A muon carries electric charge and it has spin, and a spinning charge behaves like a tiny magnet. Put a tiny magnet inside a strong magnetic field, and it does not simply snap into alignment. It precesses. It wobbles, the way a spinning top wobbles as it slows, tracing a slow cone around the direction of the field while it spins fast about its own axis. The rate of that wobble depends on how strong the muon's magnetism is, and the strength of a particle's magnetism is captured in a single dimensionless number called g. In 1928, Paul Dirac wrote down the equation that married quantum mechanics to special relativity, and the equation coughed up a prediction nobody had asked for. For a particle like the electron, g should be exactly 2. Not approximately 2. Exactly. It is not exactly 2. In 1948, Julian Schwinger worked out the first correction and found that g is slightly larger than 2, by a small amount involving the fine structure constant divided by 2 pi. That works out to roughly 1 part in 1,000. Schwinger considered the result important enough that the formula is carved on his headstone. That small excess over 2 is what physicists call the anomalous magnetic moment, and for the muon, it has a name that will come up over and over tonight. It is about 0.00116592, and it is the most precisely tested quantity in the whole of science. Not the most precisely measured, though it is nearly that. The most precisely tested, meaning the place where the theory's prediction and the experiment's answer can be laid alongside each other with more decimal places than anywhere else in human knowledge, which means it is the best place to look for something wrong. The story of measuring it is a 70-year story, and it begins in the same place we started tonight. The first 3 muon wobble experiments were run at CERN between 1959 and 1976, and across those 3 experiments the precision improved by a factor of about 1,000. Then the work moved to Brookhaven National Laboratory on Long Island, where an experiment called E821 built a superconducting storage ring 50 feet across and weighing 15 tons, filled it with a magnetic field of extraordinary uniformity, injected muons into it, and watched them wobble until they died. There is a detail in how that ring works that I find quietly beautiful, and it explains why muons can be studied at all. A muon at rest lives about 2.2 millionths of a second, which is not nearly long enough to watch it wobble thousands of times. So the experiment does not use muons at rest. It injects them at a very specific energy, about 3.09 billion electron volts, and at that energy, the muon is moving fast enough that relativity stretches its lifetime from the outside. From our point of view, standing next to the ring, each muon now lives about 64 millionths of a second, nearly 30 times longer, which is enough for it to circle the ring hundreds of times before it decays. Every single run of this experiment is a working demonstration of time dilation, used not as a curiosity but as a piece of equipment. That particular energy is not chosen for the time dilation, incidentally. It is chosen because at that exact value, the electric fields used to keep the beam focused stop contributing to the wobble entirely, which removes an entire family of possible errors from the measurement. Physicists call it the magic momentum, and it has been used since the third of the CERN experiments in the 1970s. It is the kind of design choice that looks like luck and is actually 50 years of accumulated cunning. Brookhaven published its final answer in 2004. The measurement disagreed with the best theoretical prediction of the time by about 2.7 standard deviations. In this field, that number means something specific, and it means less than you would think. 2.7 standard deviations is not evidence. It is the statistical equivalent of a raised eyebrow. It is far too small to claim anything, and just large enough that you cannot walk away from it. The Brookhaven result sat in the literature for years, unresolved and slightly irritating, like a sound in a house that you only hear at night. So they decided to do it again, harder. And the next part of this story involves one of the strangest logistical operations in the history of science. The Brookhaven storage ring could not be rebuilt from scratch. Its superconducting coils were wound to a tolerance that could not be reproduced affordably, and if you tilted the ring more than a few degrees, the coils would deform and the whole thing would be ruined. Fermilab, outside Chicago, wanted to run the experiment. The ring was on Long Island, so in the summer of 2013, they moved it. 50 feet across, 15 tons, essentially uninsurable, kept flat to within a couple of degrees the entire way. It went out of Brookhaven on a specialized transport frame, onto a barge, down the Atlantic coast, around the tip of Florida, into the Gulf, up the Mississippi, up the Illinois River, and then overland by road across Illinois in the middle of the night at walking pace, closing highways behind it. The journey was 3,200 miles. People came out and stood at the roadside at 2 a.m. to watch a white circular object the size of a house creep past under police escort, and Fermilab, to its enormous credit, published the route so that they could. Then they installed it, cooled it, tuned the field, and began. And here is where the discipline of this field shows itself, because the Fermilab team did something that sounds almost superstitious, and is in fact one of the most important ideas in modern experimental science. They blinded themselves. To turn the raw data into a final number, you need to know the exact frequency of the clock that timestamps the measurements. Without that number, the analysis produces a value that is meaningless. So the frequency was set to a secret value, written down on a slip of paper, sealed inside an envelope, and locked in 2 separate safes, one at Fermilab and one at the University of Washington. Nobody working on the experiment knew the answer. They could do every piece of analysis, argue about every correction, decide every cut in the data, and at no point could they see whether their choices were pushing the result toward the theory or away from it. You cannot fool yourself toward a preferred answer if you cannot see which direction the preferred answer is in. On the 7th of April, 2021, the envelope was opened on a video call, the frequency was applied, and the number appeared. Combined with the old Brookhaven data, the measured wobble of the muon disagreed with the standard model's prediction by 4.2 standard deviations. That was the front page of newspapers on 4 continents. 4.2 standard deviations is still not a discovery by this field's own rules, and every physicist quoted said so, and it did not matter. Because a 4.2 sigma gap in the most precisely tested number in science is exactly the shape that a new force of nature would make if it existed. But I have skipped something. I have told you that the muon wobbles slightly faster than a simple calculation says it should, and I have not told you why anybody thinks that gap is a window onto undiscovered particles, rather than just a number that happens to be slightly off. The answer to that is the single most important idea in this video, and it has nothing to do with the muon at all. It has to do with what the muon is travelling through. Part 4. The sea that pays the bill. Here is the idea. I want to go slowly with it, because everything else tonight rests on it, and because it is one of those ideas that sounds like a metaphor and is not one. When you were taught about a vacuum in school, you were probably taught it as a subtraction. Take a sealed box, pump out the air, shield it from light and radiation and stray particles. What is left is nothing. That is what the word means. Emptiness is defined as the absence of contents. Quantum field theory says that this is not achievable, not as a practical matter, but as a matter of principle. You cannot make a region of space that contains nothing, because the fields that make up the universe are present everywhere, and a quantum field cannot be perfectly still. Its lowest possible state is not zero. It has a residual restlessness that cannot be removed, in the same way that a quantum object confined in a box can never be brought entirely to rest, because being entirely at rest in a known place would violate the uncertainty principle. So empty space jitters, and that jitter has a specific form. Pairs of particles appear, borrowing energy from nothing at all, exist for an interval too short to be measured, and annihilate each other before the universe can register the transaction. An electron and its antimatter twin appearing and cancelling, a quark and an antiquark, a W boson and its opposite, all of it happening constantly everywhere, in the space between your hands, at a rate and a density that make the word emptiness actively misleading. Physicists call these virtual particles, which is an unfortunate name, because it suggests they are a bookkeeping fiction. They are not detectable. You can never catch one, extract one, or count one directly. But their consequences are measurable to more decimal places than almost anything else we know. There is a moment in the 1940s when this stopped being philosophy and became measurement, and it deserves telling, because it is the hinge on which the whole modern picture turns. In 1947, Willis Lamb and Robert Rutherford at Columbia University measured 2 particular energy levels in a hydrogen atom that Dirac's equation said should be identical. They were not identical. They were separated by a tiny amount, about 1 part in a million of the energy involved, and there was no room in the existing theory for the gap to be there. That result was carried, still warm, to a small conference on Shelter Island off the coast of Long Island in June of that year, where about 24 physicists spent 3 days on it. The explanation they arrived at, and spent the following years turning into a working theory, was that the electron in a hydrogen atom is not sitting quietly in a clean field. It is being continually jostled by the restlessness of the vacuum, and that jostling smears its position very slightly, and the smearing shifts one energy level and not the other. The gap Lamb measured was the vacuum leaving a fingerprint on an atom. Everything we now call quantum electrodynamics came out of that room and that measurement. The entire apparatus of adding up virtual particle contributions, which is what the muon calculation is, exists because a tiny unexplained gap in hydrogen forced people to take the restlessness of empty space seriously as a physical thing with consequences you could put a number on. I want to give you a picture for this, and then I want to show you the picture doing work. Imagine standing on the deck of a ship in the middle of the Pacific on a windless day. The surface is like glass, flat all the way to the horizon, and it looks like the end of the world. But you know what is underneath. Miles of black water, pressures that would crush a submarine, currents moving across whole ocean basins, and things swimming down there that no one has photographed. The flatness of the surface tells you nothing whatsoever about the volume beneath it. That is the relationship between empty space as you experience it and empty space as the equations describe it. The calm is real. The emptiness is not. Now let me put the muon into that ocean. Imagine you're riding along with a single muon inside the storage ring at Fermilab. You have just been injected. You're moving at 99.94% of the speed of light, and the 50-foot ring is bending you around in a circle nearly 100 times faster than a car engine turns over. Your own clock has been stretched by a factor of nearly 30, so from the outside you have been given a life several times longer than a muon is supposed to get. You have at most a few thousand laps. You're not travelling through nothing. You're ploughing through that ocean, and it is not passive. As you go, particles are flickering into being around you and vanishing again, and each one that appears is briefly close enough to feel you and be felt. Each one tugs infinitesimally at your spin axis. An electron and positron pair appears beside you and is gone before it can be said to have existed, and your wobble is a fraction slower for it. A pair of quarks flickers into being and back out, and your wobble shifts again. None of these things are real in the ordinary sense. All of them leave a mark. By the time you decay, a few millionths of a second later, into an electron that flies off toward a detector at the edge of the ring, the rate at which you were wobbling has been shaped by every possible way that the vacuum around you could have flickered. That is what makes this measurement extraordinary, and I want to state it as plainly as I can. The wobble of the muon is a census. Every kind of particle that exists in the universe contributes to it, whether or not we have ever seen that particle in a detector. Heavier particles contribute less, but they contribute. If there is a particle out there that we have not discovered, it is in that number. It has always been in that number. It was in Brookhaven's number in 2004, and it was in Fermilab's number in 2021. So the logic of the anomaly was clean. Calculate the wobble using every particle we know about. Measure the wobble. If the measurement is larger than the calculation, then something is contributing that is not on our list. Think about what a strange instrument that is. We built a 50-foot magnet and shipped it 3,200 miles around the eastern United States in order to weigh the things that do not exist. And it works. This is not speculative machinery. The same approach applied to the electron rather than the muon produces the single most successful prediction in the history of science. To get the electron's magnetism right to 1 part in a trillion, you have to add up thousands of distinct ways that the vacuum can flicker around it, each one contributing a smaller and smaller correction. Physicists have been computing those corrections since the 1940s, one increasingly nightmarish layer at a time, and every layer they add moves the prediction closer to the measurement. There is no honest way to read that agreement except as follows. The empty space around an electron really is doing all of those things, and we really can account for them. There is one more thing you should know about that calculation, and it will matter enormously in about half an hour, so I'm going to plant it here and leave it. Not all of the contributions to the muon's wobble are equally easy to compute. The ones involving electrons and photons are hard but tractable. You write down the possible flickerings, you compute each one, you add them up, and although the arithmetic becomes brutal, it is arithmetic. The ones involving the weak force are heavier and rarer and contribute less, so their difficulty matters less. But there is a class of contributions involving quarks, and quarks are governed by the strong force, and the strong force does not cooperate with this method at all. It gets stronger, not weaker, as things get further apart, which means the neat trick of adding up smaller and smaller corrections stops working. You cannot break the problem into a series of ever gentler nudges, because the nudges do not get gentler. That one term, the contribution of quark pairs flickering in and out beside the muon, has been the hardest number in this entire enterprise for 50 years. It is small, It is the dominant source of uncertainty in the theoretical prediction, and the entire question of whether the muon anomaly was real turned out to depend on it in a way nobody quite expected. Which brings me to the phrase I want you to hold on to for the rest of tonight. Every one of those flickering pairs is alone. The universe permits a particle and its opposite to appear out of nothing, provided the debt is repaid so quickly that no measurement could ever have caught the books out of balance. The shorter the loan, the larger the amount that can be borrowed. Nothing is created in the end. Everything is returned. But in the interval, the loan is real enough to bend the path of a muon by an amount we can measure to 9 decimal places. Empty space, then, is a sea that pays the bill. Every debt settled, always, and the settling is what shapes the world. Now hold that thought, because in the 2020s, 3 separate measurements each seem to show the books not quite balancing. We have looked at the first one. There are 2 more, and the second of them is the cleanest of all 3, because it involved a quantity that the standard model says should be exactly 1, with almost no wiggle room in the theory at all. It involved a coin that came up heads too often. Part 5. The coin that came up heads. Imagine you're handed a coin and told it is perfectly balanced. You flip it 1,000 times and it comes up heads 530 times. That is close enough to fair that you shrug. You flip it 100,000 times and it comes up heads 52,000 times. Now you stop shrugging. You have not seen the weight inside the coin. You cannot open it. But the only conclusion available to you is that there is something in there. That is the shape of the second anomaly, and it is the cleanest of the 3, because in this case the theory's prediction is not a long calculation with a hard term in it. In this case the theory says the answer is 1, and it says it with almost no room for argument. Let me set it up. Remember that the muon is an exact copy of the electron except for its mass. That is not a coincidence or an approximation. It is written into the structure of the standard model as a principle, and the principle has a name, lepton universality. It says that the weak force couples to electrons, muons and taus with identical strength, not similar strength, identical. The only reason processes involving muons ever look different from processes involving electrons is that muons are heavier, and once you account for the mass, everything else must match. That is a bedrock rule. It is not a parameter that can be tuned. If it breaks, the theory does not get adjusted. The theory gets replaced. So how do you test it? You need a process where an electron pair and a muon pair are produced by the same underlying mechanism, and you need that mechanism to be rare, because rare processes are where new physics is most likely to show itself. The place people chose is the death of a beauty quark. The beauty quark, also called the bottom quark, is a third-generation particle, and it is heavy, something like 4.5 billion electron volts, roughly 5 times the mass of a proton. It is bound up inside particles called B mesons, and those mesons are produced in enormous numbers when protons collide inside the machine under Geneva. One of the 4 big detectors on that ring, called LHCb, was built specifically to study them, and it is shaped differently from the others. Rather than wrapping the collision point in a barrel, it is a forward spectrometer, a set of instruments stacked in a line to catch the particles that fly off close to the beam direction, because that is where B mesons tend to go. Most of the time a B meson dies in ordinary ways, but occasionally, about once in a million decays, it takes a route that the standard model forbids at the simplest level and permits only through the flickering machinery we spent the last part on. The beauty quark cannot simply turn into a strange quark, but it can do it by way of a loop, a brief excursion through virtual W bosons and top quarks that exists only in the accounting, and out the other side comes a kaon plus a pair of leptons. Because that decay can only happen through the loop, it is exquisitely sensitive to what is in the loop. Anything unknown, anything heavy, anything nobody has ever detected gets to participate. The rarity is the point. It is a keyhole. It is worth sitting for a moment with what it takes to measure a ratio like that, because the number itself gives no hint of the labour underneath it. The collisions happen about 40 million times a second. Almost all of them are useless. The overwhelming majority produce nothing of interest, and there is no storage system on Earth that could write 40 million events per second to disk, so the detector has to decide in millionths of a second which collisions to keep and which to throw away forever. That decision is made by a trigger system, partly in custom electronics and partly in software, and once an event is discarded, it is gone. If your rare decay happened in a discarded event, it never happened as far as science is concerned. Out of what survives, You then have to find the specific signature, a kaon and either 2 muons or 2 electrons, with the right combined mass and the right geometry, emerging from a point slightly displaced from the collision itself because the B meson travelled a measurable distance before it died. Muons are relatively easy. They punch through everything and are caught by dedicated chambers on the outside of the detector. Electrons are harder, and that difficulty is going to matter more than anyone realised. Do that for years, across trillions of collisions, and at the end of it you have a few thousand of the decays you wanted, and you divide one set by the other, and you get a number with 3 decimal places that either agrees with the most successful theory in history or does not. Now the test. Take all the times that decay produces a muon and an antimuon. Take all the times it produces an electron and a positron. Divide one by the other. That ratio has a name, and physicists write it as R sub k. Lepton universality says that ratio must be 1, and because almost every messy detail of the strong force cancels out when you take a ratio of 2 nearly identical processes, the theoretical uncertainty on that prediction is around 1%. 1%. In a field where the hard problems usually come with uncertainties of 10 or 20%, that is a razor. They measured it. In 2014 the number came in low. Not dramatically, but low, around 0.8 rather than 1. In 2019, with more data, it stayed low. And in March of 2021, LHCb published a measurement with the full data set available at the time. The answer was 0.846. The universe appeared to be producing muons about 15% less often than the electrons, in a process that demanded exact equality. The statistical significance was 3.1 standard deviations. 3.1 is a threshold with a name in this field. It is called evidence, and it means the odds of getting a fluctuation that large by pure chance are roughly 1 in 740. It is not a discovery. Everyone involved said so, loudly, in the paper and in interviews. It did not matter. Because unlike the muons wobble, this one could not be blamed on a hard calculation. There was no hard calculation. The theory said 1, and the measurement said not 1. I want you to feel what that did to the field, because this is where the human part of the story sits. If lepton universality is broken, then there is a mechanism in nature that can tell an electron from a muon. The standard model has no such mechanism, so a new one would have to exist. The 2 obvious candidates each have a shape that people had been playing with for decades. One is a heavier cousin of the Z boson, a particle usually called a Z prime, which would couple more strongly to second-generation particles than to first, and would therefore tilt the ratio exactly the way the data was tilting it. The other is stranger, and, if it existed, more consequential, a leptoquark, a particle carrying both quark properties and lepton properties at the same time, which would allow a quark to turn directly into a lepton. That is not a small addition. Quarks and leptons have been 2 entirely separate families since the beginning of the theory, and a particle that bridges them is the kind of thing you find on the way to a grand unified theory. So the papers came, hundreds of them. Models were built, refined, named, and compared against each other. Conference sessions filled up. Doctoral students chose thesis topics on the strength of that ratio, which is a real decision about a real life. 3 or 4 years of a person's 20s spent working out the consequences of a number. And behind every one of those papers there were people. That is not a sentimental point. It is a structural one. Modern physics is not done by lone figures having insights in front of blackboards. It is done by very large numbers of specialists who each choose, in their 20s or 30s, a direction to spend a decade in. Choosing the beauty quark anomaly meant learning a particular corner of theory in enormous detail, publishing in it, being invited to speak about it, building a reputation on it, and having your name become associated with a number that had been measured 3 times and had come out low each time. None of them were foolish to do it. The number was there. It was published in a rigorous journal by a careful collaboration, with all the caveats attached. Following it was exactly what a serious person in that position should have done. And that is where I want to leave this thread for the moment, with the coin coming up heads and the room getting louder, because there was a 3rd measurement about to arrive, and it was going to make this one look cautious. The 3rd one was 7 standard deviations. Part 6. 7 sigma from a dead machine. Before we get to the 3rd anomaly, I need to explain what a standard deviation actually buys you in this field, because we are about to use a very large one, and the number is going to turn out to mean less than it sounds like. When physicists say a result is at 5 sigma, They mean something precise. They mean that if nothing new exists, and the apparent signal is pure statistical fluctuation, the chance of seeing something at least that extreme is about 1 in 3.5 million. That is the threshold this field uses before anyone is allowed to say the word discovery in public. 3 sigma, 1 in 740, is called evidence and is treated with polite suspicion. Those thresholds are high on purpose, and the reason is a subtlety with a wonderful name, the look elsewhere effect. If you check one specific energy for an excess, then a 3 sigma bump is impressive. But nobody checks one energy. You check thousands of bins, hundreds of observables, dozens of channels, and if you search enough places, some of them will fluctuate high for no reason at all. The apparent significance has to be corrected for how many places you looked, and the correction is often brutal. There is one more thing to say about sigma before we use it, and it is the single most useful piece of scientific literacy in this entire video. A sigma value measures exactly one thing: how unlikely a random statistical fluctuation of that size would be. It measures nothing else. In particular, it says absolutely nothing about whether you have made a mistake. That distinction sounds pedantic, and it is the difference between understanding this story and misunderstanding it. If your detector has a subtle bias, if your calibration is off by 0.1%, if the model you use to simulate your own equipment has an error in it, then your result can be wrong by an enormous margin, and the statistical significance will happily climb as you collect more data. More data makes a random fluke less likely. More data does nothing at all about a systematic error. It just makes you more confident in the wrong answer. Keep that in your pocket. We are going to need it twice tonight. So the convention is severe, and it exists because the field has been burned, which makes the third anomaly extraordinary, because it did not arrive at 3 sigma, or 4, or 5. It arrived at 7. On the 7th of April, 2022, the CDF collaboration published a paper in the journal Science announcing the most precise measurement ever made of the mass of the W boson. The W is one of the 2 carriers of the weak force, the heavy short-range force that governs radioactive decay and lights the first step of fusion inside the Sun. Its mass is not a free parameter of the Standard Model. It is a prediction. Once you have measured the mass of the Z boson, the mass of the top quark, the mass of the Higgs, and a handful of other quantities, the theory tells you exactly what the W must weigh, because all of these things are locked together by the structure of the electroweak theory. The W boson is also, incidentally, one of the reasons you are alive. The first step in the fusion chain that powers the Sun requires 2 protons to collide and one of them to turn into a neutron, and that conversion is a weak interaction, mediated by a W. It is an extraordinarily improbable process. A given proton in the core of the Sun waits on average billions of years for it to happen. That improbability is precisely why the Sun burns slowly enough to have kept a planet warm for 4.5 billion years rather than detonating in an afternoon. The mass of the W is one of the numbers that sets that rate. The prediction is about 80,357 million electron volts, with an uncertainty of about 6. It is worth saying plainly how heavy the W is, because the numbers in this field slide past without landing. 80,000 million electron volts is about 86 times the mass of a proton, a single force carrier, weighing as much as an entire atom of a light metal, appearing and disappearing inside a decay that takes less time than light needs to cross a nucleus. That mass is the whole reason the weak force is weak. A particle that heavy cannot reach far before the loan has to be repaid, and its reach is about 1,000th of the width of a proton. Make it lighter, and the Sun would burn differently. Make it much lighter, and there would be no Sun to burn. CDF measured 80,433.5 with an uncertainty of 9.4. That gap is 76 units wide. Against uncertainties in the single digits, it is 7 standard deviations. By the field's own published rules, 7 sigma is not a hint, not evidence, and not attention. 7 sigma is a discovery, and the thing being discovered is that the electroweak theory does not close. And there is something else about that result that made it land even harder. It did not come from the machine under Geneva. It came from the Tevatron, an accelerator at Fermilab in Illinois that had been switched off in 2011. The data had been sitting there for over a decade while a large team went through it with almost obsessive care, calibrating the detector's response against known quantities, modelling every source of distortion they could think of, checking the momentum scale of their tracking chamber against the well-measured masses of other particles. 10 years of work on a dataset from an accelerator that no longer existed. That is not the profile of a sloppy result. That is the profile of a group of people who knew exactly what they were about to claim and spent a decade trying to talk themselves out of it. Think about what a heavier W would have meant. The W mass is not an isolated fact. It is a load-bearing beam. It is tied by the equations to everything else in the electroweak sector, and if it is heavier than the theory allows, then something else is contributing to it that is not in the theory. Some additional particle participating in the same flickering loop machinery we have already met, nudging the W's mass upward the way virtual particles nudge the muon's wobble. Supersymmetric partners could do it. Additional Higgs-like particles could do it. A whole family of models that had been sitting on shelves since the 1980s suddenly had a number to explain. So by the middle of 2022, the situation was this. The muon was wobbling too fast at 4.2 sigma. The universe appeared to be favouring electrons over muons in beauty quark decays at 3.1 sigma, and the W boson appeared to be too heavy at 7 sigma from a decade of painstaking work by a collaboration with an excellent reputation. 3 quantities, 3 collaborations, 3 continents worth of hardware, 3 independent ways of pointing at the same conclusion, which is that the 17-particle chart is not the whole chart. I remember the mood of the coverage in that period, and it was not the usual cautious hedging. It was closer to relief. Particle physics had spent 20 years being told that it had found everything it was going to find, that supersymmetry had failed to appear, that the machine had confirmed the last prediction and had nothing left to do. And then, in the space of about 18 months, 3 separate doors opened at once. That is where this story is at its midpoint. So let me stop and step back and put all 3 of them on the table together, because what happened next is the actual subject of this video, and you need the pieces in front of you before it starts. Part 7. 3 doors, all open at once. Let me step back for a moment and put the pieces together, because we are exactly halfway through tonight, and the second half only works if the first half is stacked properly in your mind. Here is where we stand, as of roughly the middle of 2022. We have a theory of 17 particles that has never been caught making a clean mistake, that predicts the magnetism of the electron to about 1 part in a trillion, and that cannot derive a single one of its own 19 input numbers, cannot say why there are 3 generations of matter instead of 1, and does not contain gravity in any form. We have a machine 17 miles around, buried under 2 countries, colder than interstellar space, that spent 13 years smashing protons together 40 million times a second in order to find out what the theory was hiding. We have a fact about empty space that the theory itself insists on. It is not empty, it jitters. Pairs of particles borrow themselves into existence and pay the debt back before the universe can audit the books, and the traffic of that borrowing shapes the behaviour of everything that moves through it. And we have 3 measurements, all of which appear to catch the books out of balance. The first is a muon in a 50-foot magnet in Illinois, wobbling faster than the calculation says it should, by an amount that suggests something not on the chart is flickering beside it. 4.2 standard deviations announced in April of 2021 on the front pages of newspapers on 4 continents. The second is a beauty quark dying inside a detector under the French countryside, producing electron pairs more often than muon pairs in a process that the theory says must treat them identically. 0.846 where the answer should be 1, at 3.1 standard deviations, announced in March of 2021, and followed by hundreds of theory papers proposing particles that could tell the 2 apart. The third is the W boson, weighed with 10 years of care in data from an accelerator that had already been switched off, coming out 76 units heavier than the theory permits. 7 standard deviations, announced in April of 2022, in a journal that does not print things lightly. 3 quantities that have nothing to do with each other, a magnetic wobble, a decay ratio, and a mass. Measured by 3 different collaborations on 2 continents, using entirely different hardware, over timescales that barely overlap, and all 3 of them, at the same historical moment, pointing outward from the 17-particle chart. It is worth pausing on why 3 at once mattered so much, rather than 3 spread across 30 years. Anomalies are not rare. In a field that publishes thousands of measurements a year, a handful of 3 sigma results is not merely possible, it is statistically required. If nothing anomalous ever showed up, that would itself be evidence that somebody was rounding. So a single anomaly, taken alone, is background noise in the life of the discipline. People note it, wait for more data, and get on with their work. But 3 anomalies, in 3 unrelated quantities, arriving inside 18 months is a different kind of object. It starts to look like a pattern rather than a coincidence, and patterns are what theorists live on. If the same new particle could explain 2 of the 3, or all 3 at once, then you're no longer looking at a statistical accident. You're looking at a shape, and people tried. There were serious papers in that period attempting to build single models that would nudge the muons wobble, tilt the beauty-quark ratio, and push up the W mass simultaneously. Some of them were elegant. A heavy new boson in the right place, coupling in the right proportions, could in principle touch all 3, because all 3 are quantities that are sensitive to what flickers in a loop. If you had asked a particle physicist in 1995 what the best possible year for their field would look like, they would have described something very close to 2022. And here is the thing about that moment which I find genuinely moving, and which I want you to hold on to as we go into the second half. Nobody in this story was hoping for the theory to survive. The standard model surviving is the boring outcome. It is the outcome where the machine has nothing left to find, where the field's next 50 years are decimal places, where the young people entering it now will spend their careers making an existing number slightly more precise. Every single person working on these 3 measurements wanted the crack to be real. Their careers, their funding, their intellectual lives, and in many cases their actual love of the subject all pointed the same direction. There was also, underneath all of it, a much older ache that the 3 doors briefly seemed to soothe. The uncomfortable truth about the discovery in 2012 is that it was the last thing the theory had left to predict. Every particle on the chart was now accounted for. The machine had been built to answer one question, and it had answered it correctly in the affirmative, and there was no second question written down anywhere for it to answer next. Meanwhile, the great hope of the previous 4 decades, the family of theories called supersymmetry, had predicted a whole shadow set of partner particles that the machine should by then have been tripping over. It found none. It has still found none. So the field entering 2021 was not a field flush with success. It was a field that had confirmed its own completeness and did not know what to do about it. 3 anomalies arriving at once was not just interesting, it felt like a reprieve, which means that everything that happened next was done by people acting against their own interests, with instruments they had built themselves, on results they had personally announced. So, 3 doors, all standing open, in the same 18 months for the first time in a generation. Now let me tell you what walked through them. Part 8. Nothing walked through. The first door to close was the cleanest one, and it closed 5 days before Christmas. On the 20th of December 2022, the LHCb collaboration announced the result of a substantially improved analysis of the beauty-quark ratio. They had not simply added more data, they had gone back through the way the detector identifies electrons, and they had found a problem. Electrons are difficult. A muon is easy to recognize because it punches straight through the dense material of the detector and lands in dedicated chambers on the outside, and almost nothing else does that. An electron is lighter. It radiates energy as it bends in the magnetic field, and its signature can be imitated. Specifically, it can be imitated by hadrons, ordinary particles made of quarks, which are produced in enormous numbers in every collision and which occasionally deposit energy in a pattern that looks like an electron. The original analysis had underestimated how often that happens. The number of fake electrons in the sample was larger than the model said, and the shape of that contamination in the fit was not being described correctly. When the collaboration tightened the electron identification criteria and rebuilt the description of the leftover misidentified component, the ratio moved. They measured it in 4 different configurations, 2 ranges of momentum transfer, in 2 different B meson decays. All 4 came out consistent with 1. The coin was not rigged. The coin had never been rigged. There had been a smudge on the lens through which we were watching it land. I want to be very careful about how this gets characterized because the way it is usually told is unfair. This was not a scandal. Nobody hid anything. Nobody rushed anything. And the original result was not sloppy work. Detecting electrons in the middle of a proton collision is genuinely one of the hardest things anyone does with a machine, and the collaboration that found the error was the same collaboration that had made it. They found it themselves, in their own data, using their own detector, and they published it in a form that could not be misread, and they did it in the same week that most of Europe was going home for the holidays. Think about what that costs. Hundreds of theorists had spent years on that number. Doctoral theses had been written on models designed to explain it. Careers had turned on it. There was no external authority forcing LHCb to look harder at their electron backgrounds. The result had been published. It had been celebrated. It was in the textbooks in waiting. All they had to do was not look. They looked. This field has a graveyard, and it is worth walking through part of it, because these three are not the first. In September of 2011, an experiment called OPERA announced that neutrinos fired from the machine under Geneva to a detector under a mountain in central Italy had arrived about 60 billionths of a second earlier than light would have. The significance was 6 standard deviations. If true, it broke special relativity, which is the load-bearing structure of essentially all of modern physics. The collaboration behaved impeccably. They did not claim a discovery. They published the measurement and asked the world to find their error. In February of the following year, the error was found. A fibre optic cable connector was not fully seated in its socket, and a clock oscillator was running slightly fast. 6 sigma, undone by a loose cable. 2 senior members of the collaboration resigned. In December of 2015, both large detectors on the ring under Geneva reported an excess of events, producing pairs of photons at an energy of about 750 billion electron volts, both of them, independently. Within 8 months, roughly 500 theory papers had been written about what it might be. In August of 2016, with more data, it vanished completely. It had been a fluctuation in 2 detectors at once, at the same energy, by chance. The permanent published record of modern physics now contains a substantial literature about a particle that was never there. I tell you those 2 not to make anyone look foolish, but because they are the reason the thresholds are set where they are, and because they are the necessary background for what happened between 2022 and 2025. The second door closed more slowly and by a different mechanism. Not a discovered error, but a crowd of disagreements. The CDF result on the W boson mass could not simply be checked, because the accelerator that produced the data no longer existed. What could be done was to measure the same quantity elsewhere, with different detectors, different systematics, and different people. In 2024, the Atlas collaboration published a reanalysis of its own data and got 80,366.5 with an uncertainty of about 16. That agrees with the standard model. In September of 2024, CMS published the most precise W mass measurement ever made at the machine under Geneva, 80,360.2, with an uncertainty of 9.9. That matches the precision of the CDF measurement almost exactly, and it agrees with the standard model, and it disagrees with CDF. LHCb's measurement agrees with the standard model too, so the scoreboard, as it now stands, is that every W mass measurement in the world agrees with the prediction and with each other, with a single exception, and the exception is the most precise measurement ever made by a detector that has been switched off since 2011. The consensus interpretation is that there is an unidentified systematic effect somewhere in the CDF analysis, most likely in the calibration of the momentum scale of the tracking chamber, or in the models used to describe how the quarks inside the colliding protons share their momentum. Notice what that means in light of what I asked you to keep in your pocket. 7 sigma. The highest statistical significance any of these 3 anomalies ever reached, and it appears to have been wrong, and the sigma value never once flickered, because sigma was never measuring the thing that went wrong. The third door was the big one, and it did not close by anybody finding a mistake. It closed because the theory caught up. Remember the term I planted a while back, the one contribution to the muon's wobble that could not be computed the easy way, because it involves quarks, and the strong force refuses to cooperate. That one term, the hadronic contribution, is small. It is also, by an enormous margin, the largest source of uncertainty in the entire theoretical prediction. Everything else is nailed down. This one number was the whole argument. For 2 decades there was one accepted way to get it. Rather than computing it, you inferred it from data. You took 40 years of measurements from electron-positron colliders around the world, measurements of how often those collisions produce hadrons at various energies, and you fed them into a mathematical relationship that converts them into the quantity you need. That method is called data-driven, and in 2020 the Muon G-2 theory initiative, a large international body assembled specifically to produce one agreed number, published a consensus white paper using it. That white paper is the prediction that the 2021 measurement was compared against. That is where 4.2 sigma came from, but there was a second way, and it had been getting better for years. Instead of inferring the answer from experiment, you compute it directly by simulating the strong force itself inside a supercomputer. In 2021, a collaboration based in Budapest, Marseille and Wuppertal published exactly such a calculation, and their answer was larger than the data-driven one. Large enough that if you used their number instead, the muon's wobble stopped being anomalous. For 4 years, the field had 2 theoretical predictions that disagreed with each other, by more than either of them disagreed with the experiment. That is an uncomfortable position to be in publicly, and to their credit, nobody pretended otherwise. Meanwhile, the experiment kept running. On the 3rd of June 2025, the Fermilab collaboration published its final result, using all 6 run periods from 2018 through 2023, with roughly 21 times the data of the old Brookhaven experiment. The precision reached 127 parts per billion, better than the goal they had set themselves, and about 5 times sharper than Brookhaven had managed. It is the most precise measurement of that quantity that has ever been made, and it may stand for a long time. And in the same year, the Theory Initiative published a new white paper. By then, multiple independent lattice groups had done the hard calculation and had converged on compatible answers. The initiative adopted the consolidated lattice average as the standard model value. Here is the arithmetic that ended a 24-year story. The measured value minus the predicted value comes out to 38 in the units this quantity is conventionally written in. The uncertainty on that difference is 63. A difference smaller than its own uncertainty is not a difference. There is one honest asterisk to put on this, and I would rather give it to you than have you find it later. The lattice calculation and the older electron-positron collider data still do not agree with each other. Something is wrong somewhere, either in 4 decades of accumulated cross-section measurements, or in the systematics of the lattice simulations, or in some subtle piece of the conversion between the two. That is a genuine, live, unresolved problem, and people are working on it right now. But notice what kind of problem it is. It is a disagreement between 2 ways of calculating a standard model quantity. It is not evidence for a particle. Whichever side turns out to be right, the resolution lives entirely inside the existing theory. The muon anomaly is gone, not disproven, not overturned, not scandalous, simply resolved, by people getting better at the hardest number in the calculation, and the resolution says that the muon has been wobbling exactly as much as the 17-particle chart says it should, the entire time. So the honour scoreboard for the 2020s reads as follows: 3 doors opened, all 3 closed, nothing walked through, and if that were where this story ended, it would be a short and slightly sad video about how science corrects itself, but it is not where the story ends because of what closed the 3rd door. I have told you that the muon anomaly died when the theorists got better at the hardest term in their calculation. I have not told you what that term is a calculation of, and when you look at what that supercomputer was actually doing, the answer to tonight's question stops being about anomalies entirely. Part 9. What killed? The anomaly was stranger than the anomaly. I want to walk you into a room now, not a laboratory, a computing centre. It is a large hall filled with racks, and the racks are filled with processors, and the noise is a flat, continuous roar of cooling. There is no experiment here. There are no magnets, no beams, no particles of any kind. And what is happening inside those racks is the calculation that ended a 24-year-old anomaly in particle physics. The technique is called lattice quantum chromodynamics, and I want to describe what it actually does, because when you understand what is being computed, the entire meaning of tonight's question shifts. The strong force cannot be handled the usual way. The usual way, the one that gives us the electron's magnetism to 1 part in a trillion, works by writing down every way a process can happen, computing each one and adding them up, with each successive layer of complication contributing less than the one before. It works because the electromagnetic interaction is weak. Every additional flicker costs you a factor of about 1 in 137, so the series converges and you can stop when you run out of patience. The strong force does not do that. Its coupling is roughly 1, which means every additional layer contributes about as much as the last one, and the series never settles down. You cannot approximate your way in, so instead, people do something almost brutally direct. They take a small piece of space-time, a few million millionths of a millimeter across, and they chop it into a grid. A 4-dimensional grid, 3 dimensions of space, and 1 of time, with points spaced something like a 20th of the width of a proton apart. They put the quark fields on the points of that grid and the gluon fields on the links between them, and then they ask the computer to evaluate what the theory says the total behavior of that little box of space-time is, by generating enormous numbers of possible configurations of those fields and averaging over them, weighted by how likely the theory says each configuration is. These runs consume tens of millions of processor hours. They are among the largest scientific computations performed anywhere. There is something worth noticing about that grid before we go on, because it produces one of the stranger facts in computational physics. The box being simulated is tiny, a few femtometers across, which is a few millionths of a billionth of a meter, small enough that a single proton would nearly fill it, and time, in that simulation, is not the thing you experience. It is a fourth axis of the grid, treated mathematically almost like the other three, so that what the computer is evaluating is not a sequence of events unfolding, but a whole 4-dimensional block all at once weighted by probability. The finer you make the grid, the closer the simulation gets to the real continuous theory, and the cost rises steeply, roughly as the 5th or 6th power of the fineness. Halve the spacing and the calculation can become 50 times more expensive, which is why this took 30 years to become possible, not because anyone lacked the equations, but because the world had to build machines fast enough to sum over a box of nothing. Now here is what I need you to see. What is that computation summing over? It is summing over configurations of the vacuum. That is the entire content of the hadronic term. The reason it exists at all is that a photon travelling near the muon can briefly become a quark and an antiquark, which then re-annihilate. That pair does not exist. It cannot be detected, extracted, isolated or counted. It borrows energy from nothing and returns it before any measurement could catch the ledger open. And the muon's wobble cannot be predicted correctly unless you sum over every possible way that borrowing can happen inside a box of empty space. That is what those racks were doing. They were enumerating the ways nothing can behave. I find the human shape of this part of the story quietly remarkable too. The people who produced the lattice number were not trying to rescue the standard model. They were doing what lattice physicists have been doing since the 1970s, which is grinding away at a problem that everyone agreed was important and nobody could solve, on machines that were never quite fast enough for decades, with very little attention. The field did not consider it glamorous. There were no press conferences for incremental improvements in the systematics of a discretized gauge theory. And then, in the space of a few years, several independent groups using different lattice spacings, different ways of representing the quark fields, and different approaches to controlling their errors, all converged on compatible answers. Convergence from independent methods is the strongest thing science has. It is the same argument that made the 2012 discovery credible. 2 detectors, built by 2 teams who deliberately did not share their analysis, arriving at the same bump. The people who had spent their careers on the least visible part of the calculation turned out to be holding the answer to the field's most visible question. The anomaly did not close because the vacuum turned out to be simpler than we thought. It closed because we finally counted the ghosts correctly. I want you to sit with that for a moment, because I think it is the most interesting sentence in this entire subject, and it almost never gets said out loud. For 24 years, the muon's wobble looked like evidence of an undiscovered particle. The way that appearance was dispelled was not by finding the muon behaving normally, or by discovering an error in the magnet, or by recalibrating a detector. The wobble was always there. The measurement was always right. What changed was that a supercomputer became good enough at simulating the restlessness of empty space to account for the last few parts per billion of it. The sea paid the bill, every debt was settled, exactly as the theory said it would be, down to a precision of 127 parts in a billion. And the only reason we know that is that we built a machine capable of following the accounting. And there is a second thing hiding in that fact, which took me a while to appreciate properly. Consider what it means that the hadronic term was the hard one. That term is the contribution of the strong force, and the strong force is the one that binds quarks into protons. It is the force whose effects are least like small solid objects rattling around. Quarks cannot be pulled apart at all, because the energy in the field between them grows as you separate them until, at some point, There is enough energy in the field to simply create a new pair of quarks, and the string snaps into two new particles rather than yielding a free one. Nobody has ever seen an isolated quark. According to the theory, nobody ever can, so the piece of the calculation that resisted the take-it-apart method for 50 years was precisely the piece describing the force under which things cannot be taken apart. That is not a coincidence. It is the theory telling us, in the plainest way available to it, which picture is wrong. Think about what that implies about the thing we were calling the Standard Model. We have been treating it as a chart of parts, 17 entries, a watch with 17 kinds of gear. And in that picture, an anomaly means a missing gear, and finding the missing gear is what a door to a new reality would look like. But that is not what the theory is. The chart is a summary. The actual object is a set of fields, and the calculation that just closed the biggest anomaly of the century did not treat particles as parts at all. It never represented the muon as a small object travelling through a region. It computed the behaviour of fields on a grid, and the particle was the answer, not the input. The most precise confirmation of the Standard Model ever produced was achieved by a method in which particles are not fundamental. Let me put that another way, because it is the pivot of the whole video. For a century we have looked for cracks in the wall by taking the wall apart. Every time we found a piece that did not fit, we assumed there was a smaller piece behind it. And the crowning achievement of that method, the moment where it worked most spectacularly, was a computation which quietly assumed that there are no pieces. This is why I keep saying the anomalies were the least interesting thing in this story. The anomalies were the last gasp of the pocket watch picture. They were us asking over and over, is there another gear in here? And the answer that came back 3 times from 3 different directions was no. There is no other gear. And by the way, there were never any gears. There is a version of this story in which that is a disappointment, and I understand why. A generation of people wanted a new particle, and instead they got a better estimate of an old integral. But look at what the better estimate is an estimate of. Nobody had to add anything to reality to make the numbers agree. What had to happen was that we became capable of accounting to 9 decimal places for the behaviour of a region of space with nothing in it. That is not a smaller result than a fifth force. It is a stranger one, and it has been sitting in plain view since the 1940s, wearing the disguise of a technical term. So if there is a door here, and I do want to argue that there is, it is not on the other side of the theory. It is inside the theory, in the part we skip past because it is written in a language we do not have a picture for. Which means that before I can answer the question in the title of this video, I have to tell you what the theory actually says the world is made of. Not the chart, the thing underneath the chart. And I should warn you gently because it is late and you are comfortable. The honest version of that answer is going to take something away from you. Part 10. Open the watch. Far enough and there are no gears. Let me take you back to the pocket watch because I owe you the second half of that metaphor. We opened the brass back and found gears. We took the gears out and found smaller mechanisms inside them. We kept going. Molecules, atoms, nuclei, protons, quarks. Every layer down there were parts, and the parts had shapes and positions and were made of something. Now open it one more time. There are no gears. There are no springs, no levers, no pieces at all. There is nothing in there with a shape or a size or a surface. What the mathematics of the Standard Model actually describes, underneath the chart of 17 entries, is a small number of fields, each one spread continuously through every point in the universe, and the things we have been calling particles are not objects sitting in those fields. They are what the fields are doing. I want to be careful here, because this sounds like a poetic flourish, and it is a technical statement about how the theory is written. In quantum field theory, there is one electron field, not one per electron. One, total, filling all of space, present in the room you're lying in, present in the vacuum between galaxies, present inside the sun. An electron is a quantist excitation of that field, in the same way that a note is an excitation of a string. When we say 2 electrons, we mean the field is carrying 2 units of excitation. It is worth saying where this idea came from, because it did not arrive as a philosophical proposal. It arrived because the alternative broke. In the 1920s, quantum mechanics was written for a fixed number of particles. You had an electron, you had a wave function describing where it might be, and the number of electrons was a constant of the setup. That worked beautifully for atoms. It fell apart the moment anybody looked at high-energy processes, because at high energies particle numbers are not constant. Light turns into an electron and a positron, An electron and a positron annihilate into light. A neutron decays and produces particles that were not present a moment earlier. You cannot describe that with a theory whose basic object is a fixed count of things. So Dirac and Jordan and Pauli and Heisenberg and Wigner, across the late 20s and the 30s, rebuilt the framework so that the basic object was a field, and the count of particles became a property of the field state rather than a fixed input. Creation and annihilation stopped being paradoxes and became operations. It was not a metaphysical preference. It was the only way to write down a theory that did not contradict the experiments. This is not an interpretation. It is the reason for several facts that are otherwise inexplicable. Consider that every electron in the universe is exactly identical, not similar, identical, to the limits of measurement, in charge, mass, and magnetic moment, everywhere, always. That is a very strange thing for an object to be. 2 grains of sand are not identical. 2 hydrogen atoms are nearly identical, but you can in principle distinguish them by their history. Electrons cannot be distinguished at all, even in principle, and that indistinguishability has physical consequences that show up in the statistics of how matter behaves. The field picture explains it in one line. They are not copies of each other, they are the same kind of ripple in the same single field, and there is nothing else about them to differ in. Consider that particles can be created and destroyed. Smash 2 protons together at the energies we have been talking about, and you can produce particles that were not there before, in quantities that depend on the energy available. If particles were tiny, indestructible objects, that would be manufacturing. In the field picture, nothing is manufactured. The fields simply change configuration, and the accounting of energy and charge is preserved throughout. And consider the vacuum. If the fundamental things are fields rather than objects, then removing all the objects from a region does not empty it. The fields are still there, and a quantum field cannot be perfectly still, for the same reason a quantum particle cannot sit motionless at the bottom of a well. Its lowest state has an irreducible jitter, and that jitter is the sea we have been talking about all night. You do not have to take my word that this jitter is physically real because it has been weighed. In 1948, Hendrik Casimir worked out a consequence of it that is almost absurdly direct. Take 2 flat, uncharged, electrically conducting plates. Put them in a vacuum, parallel, a few hundred nanometers apart, which is roughly 1/100th the width of a human hair. The gap between them can only host vacuum ripples whose wavelengths fit in the gap. The space outside can host all of them. So there is more of the vacuum's restlessness outside the plates than inside, and the plates are pushed together by nothing at all. Steve Lamoureux measured that force in 1997 and found it within about 5% of the prediction. Umar Mohideen and Anushree Roy tightened it to about 1% the following year. 2 pieces of metal in an empty box drawn together by the structure of emptiness, by exactly the amount the equations say. The Lamb shift, which we met earlier, is the same phenomenon leaving a mark on the energy levels of a hydrogen atom. The magnetism of the electron, agreeing with theory to 1 part in a trillion, is the same phenomenon summed over thousands of contributions. And the wobble of a muon in a magnet in Illinois, finally matching prediction in 2025, is the same phenomenon again, accounted for at last. 4 completely different experiments, across 78 years, all measuring the behavior of nothing, all agreeing. There is one more measurement I want to give you here, because it takes the vacuum out of the laboratory and puts it in the sky. Every star you've ever seen is powered by a process that requires particles to change identity, and that changing is a field operation, not a rearrangement of parts. And every black hole, according to a calculation Stephen Hawking published in 1974, should be slowly evaporating for exactly the reason we have been discussing. Pairs flickering into being at the edge of the horizon, with one member falling in and the other escaping, so that the borrowing never gets repaid and the whole pays the difference out of its own mass. That radiation has never been observed astronomically, and it may never be, because for any black hole we know about it is absurdly faint. But the calculation is considered close to certain, and it is the same machinery, applied at the edge of the strangest object in the universe. The restlessness of empty space is not a local curiosity of accelerator physics. If Hawking is right, it is what eventually takes the universe's black holes apart. Now, I want to do something with all of that. I want you to look around the room you are in. Do not think about the walls. Think about the space between things, the gap between your hand and whatever it is resting on, the air, and then, if you remove the air, whatever is left. There is no empty region anywhere in that room. The electron field is present at every point in it, including inside your hand and inside the gap. The quark fields are present. The photon field is present, and it is not still. It is carrying the residual restlessness that pushed Casimir's plates together. The field that gives everything its mass, the one they applauded in 2012, fills that room to its corners at a value it settled into in the first fraction of a second after the beginning of the universe, and every particle in your body is heavy because of what it is doing against that background. And the solidity you feel when you press your palm down is not two surfaces meeting. There are no surfaces. It is the electron field refusing to allow two excitations into the same state in the same place, which is an abstract rule about the mathematics of the field, and which is also, physically, the reason you do not sink through your bed. You have been feeling the structure of the vacuum your entire life. You just did not have a word for it, and the word, when it arrives, turns out to be a piece of arithmetic. Here is the part that surprised me most when I first understood it properly. Almost none of your mass comes from the field they found in 2012. A proton is made of 3 quarks. Add up the masses of those 3 quarks, and you get about 1% of the mass of the proton. 1%. The remaining 99% is the energy of the gluon field binding them, plus the churning of virtual quark pairs inside. That is not a metaphor, and it is not a rounding error. Essentially, all of the weight of your body, all of the weight of this planet, all of the weight of every star you can see, is field energy in motion, not the heaviness of any substance. You're not made of stuff, in the sense you have always meant that word. You're a persistent pattern in several fields, held together by the energy of their interaction, and the pattern has been running continuously for as long as you have been alive. So we have taken the watch apart completely, and there is nothing inside it. That should feel like an ending, and I want to be honest with you. For a long time I thought it was one. But there is a whole set of things this theory of fields cannot do, and they are not decimal places, and they have been sitting in the open the entire time we were chasing anomalies in the 9th digit. Part 11. The cracks that never closed. I have spent most of tonight telling you about 3 anomalies that dissolved. I want to spend this part telling you about the ones that never did, because they are much larger, they have never been in any danger of going away, and almost none of them ever made a headline. The difference between the 2 kinds is worth naming precisely. An anomaly is the theory saying something and the world saying something slightly different. What I am about to describe is the theory not saying anything at all. Start with the largest one, which we touched on early and then walked past. The standard model does not contain gravity. There is no version of it that does. Every attempt to write gravity into the same framework as the other 3 forces produces a theory that gives infinite answers to finite questions, and the mathematical trick that removes those infinities everywhere else does not work here. This has been known since the 1930s. It is not a fringe concern or a matter of taste. The theory that describes the contents of the universe has nothing to say about the force that arranged the universe into galaxies and holds you in your bed. There is a way of feeling the size of that emission that I find works better than the words. The lightest thing in the universe that you can hold is a refrigerator magnet, and it will hold a piece of paper up against the gravitational pull of the entire Earth. All of it. 6,000 billion tons of rock and iron, pulling downward, and a small piece of ceramic wins. That is a real observation about the relative strength of 2 of the 4 forces, and it is not a small mismatch. Gravity is weaker than electromagnetism by a factor of about 10 followed by 36 zeros. Nobody knows why. It is one of the oldest open questions in physics, and it does not appear anywhere in the 17-entry chart because the chart does not contain gravity to compare anything to. We do have a theory of gravity, of course. It is general relativity. It is beautiful, and it has passed every test anybody has devised for it, including tests it had no business passing, like the detection of gravitational waves from colliding black holes. But it is a classical theory. It describes space-time as a smooth, continuous thing, and quantum mechanics says nothing is smooth and continuous at small scales. Where the 2 descriptions overlap, at the center of a black hole and in the first instance of the universe, physics as a whole simply stops producing answers. That is not a crack. That is a missing wall. Now the second one. Add up all the matter in a galaxy that we can see, every star, every cloud of gas, every dust lane. Then measure how fast that galaxy is rotating. The 2 do not match, and they do not miss by a little. Galaxies spin far too fast for the gravity of their visible contents to hold them together. They should have flung themselves apart long ago. Vera Rubin's rotation curve measurements in the 1970s made this undeniable, and everything since has confirmed and sharpened it. Colliding galaxy clusters where the mass and the visible gas end up in different places, the pattern of the earliest light in the universe, the way galaxies bend the light of things behind them. The conclusion is that about 5/6 of the matter in the universe is something we have never detected in any laboratory. 5 to 1. The 17-particle chart describes the minority ingredient, and it is not for lack of looking. There have been detectors a mile underground in old mines, inside mountains, under Antarctic ice, filled with ultra-pure xenon or argon, shielded from every known source of interference, waiting for one of these particles to nudge one nucleus. Some of those experiments have been running for decades. The most popular candidate, a heavy, weakly interacting particle that would have been produced in the early universe in exactly the right abundance, has been searched for so thoroughly and found so absent that the field has begun looking in entirely different directions. It is worth pausing on how thoroughly that particular door has been knocked on, because the emptiness of the search is itself a result. There is an experiment in Italy called Dharma that has been reporting, for more than 2 decades, a yearly rhythm in its detectors, slightly more events in June than in December, which is exactly what you would expect if the Earth were moving through a stationary cloud of dark matter and our orbital motion added to or subtracted from the wind depending on the season. The statistical strength of that signal is enormous, well beyond the discovery threshold, and it has been sustained for over 20 years, and no other experiment has ever reproduced it. Several have been built specifically to test it, using the same detector material to remove that as an excuse. They see nothing. Nobody has produced an accepted explanation of what Dharma is seeing, and nobody accepts it as dark matter. It sits there, decades old, unresolved, a reminder that a very large sigma value and a true result are not the same object. Then there is the third one, which is larger still. About 68% of the energy content of the universe appears to be something that makes space expand faster over time. We call it dark energy, which is a name rather than an explanation. The standard model has no candidate for it. When people try to estimate what the vacuum energy should be from quantum field theory directly, the answer comes out too large by a factor of about 10 followed by 120 zeros. That is the worst quantitative prediction in the history of physics, by an enormous margin, and it has been sitting there unsolved for decades. Notice that this one is not a separate problem from the C we have been discussing all night. It is that C asked a slightly different question, giving an answer that is wrong by more orders of magnitude than there are atoms in a galaxy. The fourth one is my favourite, because the theory made a clear prediction and was cleanly wrong, and everybody now behaves as though this is fine. The standard model, as originally written, says neutrinos are massless. In 1998, the Super Kamiokande detector in Japan, a tank of 50,000 tons of ultra-pure water, watched by thousands of light sensors a kilometre underground, showed that neutrinos produced in the atmosphere change from one type into another as they travel. A few years later, the Sudbury Neutrino Observatory in Canada showed the same for neutrinos from the Sun, resolving a puzzle that had been open since the 1960s. Changing type requires mass, therefore neutrinos have mass. Therefore the model as written is wrong. You can patch it. People have. But every patch you can write down brings its own questions with it, including whether the neutrino is its own antiparticle, which nobody yet knows. And the masses involved are absurd. The best current bound from an experiment in Germany weighing the energy of electrons emitted in tritium decay puts them below about 0.8 of an electron volt, which means the heaviest particle on the chart is at least 200 billion times heavier than the lightest. Nothing in the theory says why. The fifth one is the reason there is anything here at all. In the early universe, matter and antimatter should have been produced in equal amounts and should have annihilated completely, leaving a universe of light and nothing else. Instead, there was a surplus of matter, of roughly 1 part in a billion, and everything that exists is built from that leftover. The standard model does contain a mechanism that treats matter and antimatter slightly differently. It was discovered in 1964 and it is real. It is also far too small, by many orders of magnitude, to produce a surplus of 1 in a billion. Something else had to happen. We do not know what, and there are more. Why the mass of the particle they found in 2012 is as small as it is, when the quantum correction should drag it up toward the energy scale where gravity becomes strong, is a problem serious enough to have its own name, and to have motivated 4 decades of theories that have not panned out. Why the strong force does not violate the matter-antimatter symmetry when there is no reason for it not to is another. Look at that list. Gravity, absent. Most of the matter, unidentified. Most of the energy, unexplained and mispredicted by 120 orders of magnitude. Neutrino mass contradicting the original theory outright. The existence of matter itself, unaccounted for. I want to make sure the shape of this is clear, because I think it is genuinely the most important thing in this video after the vacuum. For about 15 years, public interest in fundamental physics has been organized around anomalies. Is the muon wobbling wrong? Is the W too heavy? Is the coin rigged? Those are exciting because they have a yes or no answer and a number attached, and they can be reported in a paragraph. Meanwhile, the actual state of the field is that we cannot say what most of the universe is made of. We cannot write down a theory containing all 4 forces, we cannot explain why there is matter, and we cannot derive a single mass on our own chart. Those are not close calls in the 9th decimal place. Those are entire categories of thing about which the most successful theory in history is silent. The anomalies were never where the door was. The anomalies were the doorbell, and we spent 15 years standing on the porch listening for it, in front of a house with no roof. None of those are anomalies. Every one of them is a silence, and every one of them has been there the entire time. Which raises the obvious question, and it is the last question we have to deal with before I can answer the one in the title. If the theory is this incomplete, why has the machine under Geneva not found the answer? What would a door out of this actually look like, and how hard have we knocked? Part 12. What a door would actually look like. If there were a literal door out of our 3 dimensions, this is what it would look like, and this is how hard we have knocked on it. Start with the idea, because it is older and more respectable than its reputation. In 1919, a German mathematician named Theodor Kaluza sent Einstein a paper suggesting something odd. Write general relativity in 5 dimensions instead of 4, he said, and something remarkable falls out. The extra pieces of the equations turn into Maxwell's equations for electromagnetism, for free. 2 forces, unified, at the cost of 1 dimension nobody could see. Einstein sat on the paper for 2 years, apparently torn, and then helped get it published. In 1926, Oscar Klein added the crucial idea about why nobody notices the extra dimension. It is curled up, wrapped into a circle so small that nothing we can do reveals it. Here is the picture everybody uses, and it is a good one. Picture a garden hose stretched across a lawn, seen from a 3rd-floor window. From up there it is a line. An ant walking on it, as far as you can tell, has one choice, forward or back. Walk down to the grass and the hose has thickness. The ant can also walk around it in a small circle, and that direction was always there. It was invisible from a distance because it was small and closed. The proposal is that our universe is like that hose. At every point in the room you're in, there may be additional directions, curled into shapes far too small to enter or detect, and everything we call space is the part that happens to be large. Modern string theory needs 6 or 7 of them, folded into geometries with names most physicists cannot draw. But the versions that mattered for our story tonight are different, and they came from a specific frustration. In 1998, 3 physicists proposed that some extra dimensions might not be absurdly small. They might be as large as a millimeter, and the reason nobody had noticed is that the particles we're made of are stuck to our 3-dimensional sheet and cannot leave it, while gravity can. In 1999, Lisa Randall and Raman Sundram published a different version, with a warped extra dimension, which was mathematically more elegant and equally testable. The payoff of those models is that they answer the refrigerator magnet question. Gravity is not weak. Gravity is exactly as strong as everything else, and it looks weak to us because it leaks. It spreads out into dimensions we do not occupy, and we experience only the fraction that stays. That is a real hypothesis. It makes real predictions, and so it was tested. The first test is beautifully small. If gravity leaks into extra dimensions of a certain size, then at distances comparable to that size, the familiar inverse square law of gravity must fail. So in a basement laboratory at the University of Washington in Seattle, a group has spent decades building instruments to check. Picture the apparatus. A thin pendulum hangs from a tungsten fibre finer than a human hair, inside a chamber shielded from air currents, from temperature drift, from the electrical fields of nearby equipment, and from the vibration of trucks on the road outside. Below it sits a heavy disc, drilled with a ring of holes. As the disc turns, the gravitational pull on the pendulum rises and falls very slightly, and the fibre twists by an angle measured in billionths of a radian. There is no beam. There is no collision. There is a piece of metal hanging on a wire in a quiet room, and someone watching it turn. They have pushed that measurement down to separations of about 52 micrometers, which is roughly the width of a fine human hair. Newton's law holds. Nothing deviates. I want to stay in that basement for a moment, because the contrast with the tunnel under Geneva is the whole point of it. One search costs billions of euros, employs thousands of people across dozens of countries, and requires the coldest extended region in the known universe. The other is a wire, a weight, a shielded box, and a very great deal of patience. They are asking the same question from opposite ends. Is gravity what we think it is at scales we have never checked? And the small one has an advantage the big one does not. It does not depend on any model of what happens in a collision, or on simulating the response of a detector with 100 million channels. It depends on whether a pendulum twists. There is almost nothing between the measurement and the answer. When that experiment says the inverse square law holds down to the width of a hair, there is very little room left for interpretation. The second test was the machine we have spent all night inside. If some versions of these models were right, then at high enough collision energies the machine under Geneva should produce microscopic black holes, or particles called Kaluza-Klein gravitons that carry momentum in the hidden directions, and appear to us as missing energy flying off in nowhere. Both were searched for thoroughly, in enormous datasets, over more than a decade. Nothing. No micro-black holes, no graviton signatures, no missing energy of the right shape. While we are here, let me deal quickly and honestly with the version of this that circulates online, because it deserves a straight answer rather than a sneer. The claim that the machine is opening portals draws its energy from three real things, misread. It is true that physicists genuinely search for evidence of extra dimensions there, so the topic is not invented. It is true that there is a statue of the Hindu deity Shiva as Nataraja, the lord of the dance, standing outside one of the buildings, which was a gift from India, a member state, presented in 2004 with a plaque quoting a metaphor about the dance of subatomic particles. And it is true that in 2016, a video circulated showing a hooded mock ritual in one of the courtyards, which turned out to be a prank staged by people with site access, and which the organisation investigated internally. The science answer is simpler than any of that. The total energy of a collision there is about 13.5 trillion electron volts. That sounds enormous, and per particle it is. In ordinary terms, it is roughly the kinetic energy of a mosquito in flight, concentrated into a space smaller than a proton. Cosmic rays strike the upper atmosphere of this planet at energies millions of times higher, constantly, and have done for 4.5 billion years, and the sky is still there. The same argument answers the older fear about black holes, which produced actual lawsuits before startup and 2 formal safety reviews. If collisions at these energies made stable black holes, then cosmic rays hitting neutron stars, which are far denser than Earth and have been bombarded for billions of years, would have eaten them long ago. Those stars are still where we left them, and the shutdowns that are supposed to be suspicious are published years in advance, long maintenance periods for upgrades, plus a technical stop each winter, partly because electricity in that part of Europe is more expensive and more strained in the cold months. So the honest verdict on doors is this. We proposed several. We built instruments of extraordinary delicacy to test them, from a 17-mile ring under 2 countries to a wire in a basement in Seattle. And every one of those searches came back empty. That includes the biggest hope of all, supersymmetry, the theory that gave the field its direction for 40 years, predicted a shadow partner for every particle on the chart. In its simplest and most motivated forms, the machine should have found them by now. It has excluded them across an enormous range and found nothing. It is worth being precise about what has and has not been ruled out, because this is a place where people overstate in both directions. Extra dimensions are not disproven. Nothing in that list rules out dimensions curled up at the scale string theory actually prefers, which are so small that no conceivable machine could probe them directly. What has been ruled out is the range where they would have been discoverable, and specifically the versions that were invented to explain why gravity is weak. Those had a testable size, precisely because they were designed to solve a problem, and the test came back negative. That is a distinction with a moral in it. A hypothesis becomes vulnerable exactly to the degree that it explains something. The extra dimensions that could have answered the refrigerator magnet question were the ones we could go and check, and so they are the ones that are gone. The versions that remain are safe because they predict nothing we can reach. There is a way of hearing all of that as failure. I want to suggest a different reading. An empty search is a result. It is a wall we now know the location of, and the people doing it are still going. A major upgrade will roughly multiply the machine's data by a factor of 10 through the 2030s, and there is a serious proposal for a successor ring, more than 90 kilometers around, which would take most of a century to build and pay off. But if you have been listening carefully, you already know that none of that is where I think the answer is, because we have been looking for a door in the walls of the room, and the thing this entire night has been circling is that the room is not made of anything. Part 13. The sound of nobody noticing. So, did they open the door to a new reality? I promised you a plain answer and I am going to give you one, but it comes in 3 parts, and they do not agree with each other, which is the honest shape of the thing. The first part of the answer is no. Nothing walked through. Every door that was announced in the 2020s has closed. The beauty quark ratio went back to 1 when a background of misidentified electrons was properly accounted for, 5 days before Christmas in 2022, by the same collaboration that had announced it. The W boson mass measurement that stood at 7 standard deviations is now an outlier among 5 measurements that agree with the prediction and with each other. And the muon anomaly, which ran for 24 years across 2 laboratories and 3 continents, ended on the 3rd of June, 2025, with a final measurement of extraordinary precision and a theoretical prediction that had walked over to meet it. Experiment minus theory, 38 plus or minus 63. A difference smaller than its own uncertainty is not a difference. No new particle has been found at that machine since the 4th of July, 2012. Not one. If you came here for a 5th force, I do not have one for you, and neither does anybody else, and anyone who tells you otherwise is selling something. That is the first part of the answer, and if you stop there, this is a story about a field that got excited 3 times and was wrong 3 times. I want to give the people in this story their due before I go further, because the first part of the answer is usually told as an embarrassment, and it is very nearly the opposite. Consider what actually happened. 3 results that a field desperately wanted to be true were each dismantled, and in every case the dismantling was done by the people who stood to lose the most. The collaboration that found the electron background error was the collaboration that had published the anomaly. The theorists who revised their own consensus number in 2025 revised it in the direction that erased the discrepancy their field had been living on for 2 decades. Nobody made them. There was no regulator, no external audit, no penalty for leaving it alone, and they had every reason to leave it alone. The boring outcome is professionally worse for almost everyone involved. The theory surviving means the next 50 years are decimal places. These are people who chose this work because they wanted the universe to be stranger than the chart, and one after another they published the results that said it was not. There is not much else in public life that works like that. When someone tells you that science is just another belief system, this is the specific thing they are failing to account for, a discipline that built formal machinery, including sealed envelopes in safes in 2 states, for the express purpose of stopping itself from believing its own most exciting results. But here is the second part, and it is the one I actually believe. Yes. A door opened. It was never the anomaly. Look at how the biggest of the 3 was closed. It was not closed by a better magnet or a cleverer detector or a recalibration. It was closed by a supercomputer taking a box of empty space a few millionths of a billionth of a meter across, chopping it into a grid and summing over every way that nothing could behave inside it. That is what the hardest term in the calculation was. It was an accounting of the sea, and when the accounting was finally complete, the muon's wobble matched to 127 parts in a billion. The sea paid the bill. Every borrowed pair returned, every debt settled, and the settling is what shapes the world. That is the load-bearing fact of modern physics, and we discovered it not by finding something new, but by getting good enough at counting things that do not exist, which means the picture we have been carrying for 400 years is finished. There is no watch. There are no gears. There is nothing in there with a shape. There are fields filling everything, and their restlessness is not a background detail against which events happen. It is the mechanism. 99% of your mass is the energy of a field in motion. The solidity of the floor is a rule about how a field arranges its excitations. The reason you are heavy at all is that you are dragging against something that fills the room all the way to the corners and has since the first fraction of a second after the universe began. If that is not a new reality, I do not know what would qualify. It is not next door. It is not through a portal. It is the room, correctly described, and the description has almost nothing in common with the way it feels to be in it. And now, the third part of the answer, which is the one I have been holding since the first minute of tonight. Go back to the auditorium, summer morning, 2012. Students who slept on the floor outside the doors, 2 teams who deliberately did not speak to each other, showing the same bump at the same energy. An 83-year-old man taking off his glasses to wipe his eyes, 48 years after he wrote the paper. And a room full of the most careful people on earth, standing, applauding. Every person in that room could have written the mathematics of a field on a napkin for you. They all knew what had been confirmed. What had been confirmed was that empty space is not empty, that there is something present at every point in the universe, including the point where each of them was standing, and that everything they had ever touched or been made of was heavy because of it. They applauded it as a completion, the last piece, the end of a book. I do not think they were wrong to celebrate, and I want to be careful not to be smug about it, because I would have clapped too. But I have thought about that morning for a long time now, and what strikes me about it is not that anyone made a mistake. It is how easy it turns out to be to verify something enormous and file it as an ending. There is one more thing about that morning that I keep coming back to. The field they confirmed did not switch on in 2012. It has been there the whole time. It settled into its value somewhere in the first fraction of a second after the beginning of everything, before there were atoms, before there was light that could travel freely, and it has been filling every cubic inch of the universe ever since, without interruption, through the formation of the first stars and the collapse of the first galaxies, and the 4.5 billion years this planet has been going around its sun. It was present in the room while they applauded. It was present in the lungs of everyone clapping. What happened that morning was not that something began. It was that a species living inside a thing finally measured it, and the measurement took 30 years and 8,000 people, and a whole 17 miles around under 2 countries. The door was already open. It had been open since the 1930s, in the mathematics, waiting for somebody to look at it as a description of the world rather than a piece of machinery. And on the morning it was finally confirmed by experiment, twice independently, what filled the room was the sound of nobody noticing. The 3 anomalies that came afterward were not the story. They were us, knocking on the walls of a room we were already standing inside, looking for a way out of a house we had not yet understood we were made of. So here is where that leaves us tonight, and I want to leave it as a question rather than a conclusion, because I do not think it has an answer yet. We now have a description of the universe in which there are no things, only fields and their excitations, and a ground state that never rests. That description predicts the wobble of 1 unstable particle to 9 decimal places. It also cannot tell us what 5/6 of the matter is, or what 68% of the energy is, or why there is any matter at all, or how gravity fits, or why the electron weighs what it weighs. The most accurate description ever produced by our species is simultaneously silent about most of what exists, which raises something I find myself turning over on nights like this one. If the anomalies were never the door, and the vacuum was the door all along, and it has been standing open in the equation since before anyone alive today was born, then the real question is not whether the universe is stranger than we imagined. It is how many other doors we have already opened, written down, checked, published, and applauded, without once feeling the draft.